okay. Okay, sorry for the small inconvenience. So now look at the very first question in today's class. Look at the question, MSQ type of question, asking like this: which of the following statements is or are correct? Isothermal work is the least work of a reciprocating compressor. Absolutely correct. Isothermal work is the least work of a reciprocating compressor, whereas isentropic work is the least work of a rotary compressor like Roots blower, centrifugal compressor, axial flow compressor, etc. That means isothermal process is the ideal process for all reciprocating compressors, whereas isentropic process is the ideal process for all rotary compressors. This is the reason why the performance of a reciprocating compressor is decided in terms of isothermal efficiency, whereas the rotary compressor efficiency is measured in terms of the performance of rotary compressor is measured in terms of isentropic efficiency. Anyhow, option A absolutely correct. Look at the B, Cp, that is specificated constant pressure and specificated constant volume, both are equal for water at 4 degrees centigrade. Absolutely correct. Strictly speaking, the Cp of the liquid differing from the Cv of the liquid, but the difference between the Cp and Cv for the liquids is very small, that's why we are ignoring. But strictly speaking, only for water at 4 degrees centigrade, Cp exactly equal to Cv. That's why the water is taken as ideal liquid or inviscous liquid only at 4 degrees centigrade. Remember, the water is maintaining the highest density at 4 degrees centigrade, where the Cp equal to Cv. A correct, B also correct. Look at the C. Availability of a system at a state is decided with respect to absolute zero state. Absolutely wrong. The availability of a system is decided with respect to standard atmosphere or dead state. Dead state is the standard atmospheric air state, not absolute zero state. Availability is always decided with respect to atmospheric state, roughly around 300 Kelvin, not absolute zero state. At absolute zero state, temperature is 0 Kelvin, right? Minus 273.15 degrees centigrade. Lenoir cycle is the theoretical cycle for ramjet engine. Wrong. Lenoir cycle is the theoretical cycle for pulse jet engine, not ramjet engine. Therefore, D also absolutely wrong. A and B are absolutely correct. Understood clearly? Yes. Then look at the next one. Look at the next one. Which of the following statements is or are correct? Flow work is a thermodynamic system property. Absolutely correct. You know, flow work means product of pressure and specific volume is the flow work. Since V is the specific volume, it can be also written as pressure by density, because reciprocal of the density is the specific volume. P by rho is the flow work. The same quantity we are calling as flow energy or pressure energy with the Bernoulli equation. Anyhow, this is the pressure energy, it is coming under property of the system. Whereas the displacement work is the PdV, that is also called non-flow reversible work. And steady flow work is minus VdV. These two are not coming under properties of the system. This is the work interaction formula for a closed system. This is the work interaction formula for a steady flow device. Whereas flow work, though you are pronouncing the quantity PV as a flow work, that is coming under thermodynamic system property. Anyhow, A is absolutely correct. Look at the B. Heat is stored in solids, liquids and gases. Absolutely wrong. You know, heat is a transient quantity. It cannot be stored in a body. It is always appearing only at the boundary due to temperature difference. Remember, heat and work are not storable forms of, they cannot store. Heat and work cannot be stored in a body or in a solid or liquid or gas. They are appearing only at the boundaries. That's why heat and work are coming under boundary quantities. They are not coming under storable energies. B is absolutely wrong. Next, for the flow maintains zero work transfer and zero heat transfer, the change in pressure and change in velocity are reciprocal to each other. Absolutely correct. C is correct. The flow maintains zero work transfer and zero heat transfer. The change in pressure and change in velocity are reciprocal to each other. It is like this. Let us take the steady flow energy equation. Per kg of the material, steady flow energy equation is Gz1 plus C1 square by 2 plus H1 plus Q is equal to Gz2 plus C2 square by 2 plus H2 plus H2. For the flow maintaining zero heat transfer, Q equal to 0 and plus work transfer, plus work. Zero work transfer, W equal to 0. For the flow maintains zero heat transfer and zero work transfer, right? You know, nothing is spoken regarding the elevation. Assume elevation difference is negligible. Then it becomes C1 square by 2 plus H1 is equal to C2 square by 2 plus H2. Can also be written as C2 square minus C1 square divided by 2 is equal to H1 minus H2. H1 minus H2. It can be also written as CdC is equal to minus dH. You integrate it on both sides and apply the limits from 1 to 2, you will get the same relation. Integral CdC is the C square by 2. Integral CdC is the C square by 2. Apply the limits from 1 to 2, C2 square minus C1 square by 2. Similarly, integral dH equal to H. Apply the limits from 1 to 2, H2 minus H1. But here H1 minus H2 is there. That's why I wrote minus dH. But what is the enthalpy general formula? As you know, enthalpy H equal to sum of the internal energy and flow energy or flow work. It can be also written as dH equal to du plus pdv plus vdp plus vdp. dH equal to, as you know, du plus pdv is the del q plus vdp. But given condition is flow maintaining zero heat transfer, del q equal to 0. When del q equal to 0, dH equal to vdp. Since V is the specific volume, is written as reciprocal of density, therefore dH equal to dP by rho. dH equal to dP by rho. Then CdC is equal to minus dP by rho, or dP by dC is equal to minus rho C. Change in pressure dividing by change in velocity is negative, because Cb the velocity never be negative. Change in velocity may be either positive or negative or 0. But the quantity velocity is always a positive quantity. Similarly, density also a positive quantity. Change in density may be either positive or negative or 0. Since rho is the positive quantity, C is the positive quantity, but dP by dC is negative. dP by dC negative means when the change in pressure is positive, change in velocity is negative and vice versa. From that I can conclude that when the flow is maintaining zero heat transfer and zero work transfer with negligible elevation difference, the change in pressure and change in velocity are always reciprocal. That means in a duct, when the pressure of the flow is increasing, that increase in pressure is the representation of decrease in velocity or decrease in kinetic energy. Anyhow, that statement, second statement, once again let me read it. For the flow maintains zero work transfer and zero heat transfer, the change in pressure and change in velocity are always reciprocal to each other. Correct. Joule-Thomson coefficient is greater than 0 for ideal gas. No. Joule-Thomson coefficient mu Jt is equal to dou T by dou P at constant enthalpy. The fellow Joule-Thomson coefficient is 0 for ideal gas. For ideal gas. But it is given greater than 0 for ideal gas. Option D is absolutely wrong. Then A and C are correct. A and C are correct. Understood clearly? Yes. Then let us take the another question. Look at this one. Which of the following statements is / or are correct for ideal gas? For ideal gas. For isobaric process means what? Constant pressure process. Heat transfer equal to change in enthalpy, absolutely correct. The amount of heat transfer is equal to change in enthalpy for constant pressure process. A is correct. Heat transfer Q equal to du for isothermal process. No. For ideal gas in the isothermal process, change in internal energy du equal to 0. It is clearly given that for ideal gas. So B is wrong. B is wrong. Heat transfer Q equal to work transfer. Heat transfer Q. What is the heat transfer Q equal to? Work transfer plus change in internal energy. Here change in internal energy is 0. Therefore, heat transfer is equal to work transfer for isothermal process. But given that heat transfer equal to change in internal energy, that's why it is wrong. Q equal to work. Heat transfer equal to work transfer for isochoric process. No, for isochoric process means constant volume process. For constant volume process, work done equal to 0. Heat transfer Q equal to du. Therefore, C also wrong. C also wrong. Heat transfer Q equal to 0 for isenthalpic process. Isenthalpic process means throttling process. Throttling process is adiabatic process. Steady flow adiabatic process, but it is irreversible process. For throttling process, enthalpy remains constant. That's why the throttling process you are also called isenthalpic process. Since the throttling process or isenthalpic process is adiabatic process, heat transfer is 0. D is absolutely correct. A and D are correct. Are you following clearly? Yes. Similarly, look at the next one. It is asking like this. Which of the following statement is / or are correct? Air is the refrigerant for Bell-Coleman cycle. Absolutely correct. Bell-Coleman cycle is the reversed Brayton cycle which is coming under air refrigeration cycle. The Bell-Coleman cycle and reversed Carnot cycle, of course, bootstrap air refrigeration system. These are all maintaining the air as the working fluid. Bell-Coleman cycle is the air refrigeration cycle which is coming under reversed Brayton cycle or reversed Joule cycle, which is maintaining two isentropic process and two isobaric process. So option A absolutely correct. B. Joule-Thomson coefficient is negative for the warming process. Warming process means temperature increases. But the throttling process, Joule-Thomson coefficient is for throttling process. In the throttling process, pressure is continuously decreasing. For the warming process, for the warming region, in the throttling process, Throttling process is for dropping the pressure. dP always negative. Frictional pressure drop is happening in the throttling process. Warming process means dT, warming means temperature increases. dT is positive. Then what is the Joule-Thomson coefficient? Joule-Thomson coefficient mu Jt, Joule-Thomson coefficient mu Jt is equal to dou T by dou P at constant enthalpy. For the warming process, dou T is positive, dou T is positive, dou P is negative. Therefore, Joule-Thomson coefficient is negative for the warming region in the throttling process. That's why the B, Joule-Thomson coefficient is negative for the warming process. Absolutely correct. B correct. Next, R134A, it's a kind of refrigerant, is CFC kind of refrigerant. No, it is HFC kind of refrigerant. The refrigerant which is maintaining chlorine atoms and fluorine atoms is coming under chlorofluorocarbon kind of refrigerant, simply pronounced as CFC refrigerant. But R134 does not have any chlorine atoms. That's why it is coming under HFC refrigerant. It is like this. R134, R134. General designation for a refrigerant is Rm-1, N+1 and Q. Okay. Chemical formula Cm, Hn, Clp, Fq, where M equal to number of carbon atoms, N equal to number of hydrogen atoms, P equal to number of chlorine atoms, Q equal to number of fluorine atoms. Okay. The relation between these atoms is N plus P plus Q is equal to 2 into M plus 1. Okay. Now let us decide the chemical formula for this to decide the scientific name. For M-1, equate it. M-1 must be equal to 1. From this I can write that M equal to 2. N plus 1 equal to 3. N plus 1 equal to 3. Therefore, N equal to 2. And Q equal to 4. Q equal to 4. Q equal to 4. Unknown value P. P is the number of chlorine atoms. For deciding the number of chlorine atoms, you substitute here N equal to 2, N equal to 2 plus P unknown value plus Q value how much? 4 is equal to 2 into, look at the M value 2, 2 plus 1, 2 plus 1 is 3 into 2 6, right? Left side 6, right side 6, P equal to 0. Number of chlorine atoms, P equal to 0, chlorine atoms 0. Then what is the chemical formula? Cm, Cm is C2, Hn, Hn is 2, Clp 0, F4, C2, H2, F4. It is having only hydrogen and fluorine atoms. That kind of refrigerant is called hydrofluorocarbon. Okay. So it is having no chlorine atoms. That's why it is not coming under chlorofluorocarbon kind of refrigerant. That's why I opted C is wrong. Look at the D. COP of vapor compression system increases with subcooling due to decrease in compression work. Undoubtedly, because of the subcooling with vapor compression refrigeration, VCR means vapor compression refrigeration. Because of the subcooling in vapor compression refrigerant system, COP increases due to increase in refrigeration effect, not due to decrease in compression work. COP increases because of the subcooling. That is not due to decrease in compression work. That is due to increase in refrigeration effect. Therefore, D is absolutely wrong. Therefore, A and B are correct. Are you following clearly? Yes. Then look at the next one. Yes, it is the NAT type question, numerical answer type question. Look at this one. in the vapor compression cycle shown in the figure, look at the figure, it is one of the gate problem shown in the figure. The evaporating and condensed temperatures are 260 Kelvin and 310 Kelvin. No, evaporation is happening at low temperature, that is given as 260 Kelvin, and condensation is happening at high temperature given as 310 Kelvin. That means from the diagram I can say T2 equal to T3, that is equal to 310 Kelvin, and T1 equal to T0. Of course, this is state 4, right? T1 equal to T0, that is equal to 260 Kelvin. That is the data which is given. Okay. Respectively, the compressor takes in liquid vapor mixture. The compressor, that means liquid vapor mixture is entering to compressor, wet vapor. Okay. At state 1, and isentropically compresses it to dry saturated vapor condition. Look at the diagram. Wet refrigerant is entering to compressor. During the compression process, isentropically the wet refrigerant is becoming the dry saturated refrigerant. Okay. Next, the specific heat of the liquid refrigerant is 4.8 kilojoules per kg Kelvin. Specific heat of liquid refrigerant 4.8 kilojoules per kilogram Kelvin, that is given, and may be treated as constant. That specific heat at constant pressure of the liquid is remaining constant. The enthalpy of the evaporation for the refrigerant at 310 Kelvin is 1054 kilojoules per kilogram. Look at the diagram. During the 2 to 3 process, condensation is happening. The kind of heat transfer during the condensation? Latent heat. That latent heat during the 2 to 3 process given, 1054 kilojoules per kilogram. Okay, that condition is given. Okay, next. The difference between the enthalpies of state points 1 and 0, you are asked to decide what is the enthalpy difference between 1 and 0. H1 minus H0 is equal to how much? That is the question. Look at the 1 to in 0 to 1 process, temperature remains constant. Na? You know, entropy ds equal to del q by t. The del q equal to TDS, heat transfer equal to T into ds for the reversible process, because the ds equal del q by t only for a reversible process. Here a 2 to 3 process is a reversible process and 0 to 1 process also a reversible process. Therefore, I can write that this del q equal to H2 minus H3 is equal to T into S2 minus S3. Otherwise, should be very careful while we are discussing in the limited space. For the 2 to 3 process, where the temperature is maintained constant, I can say that H2 minus H3 equal to T into T during that process into S2 minus S3. Similarly, this T I can say T2. Similarly, H1 minus H0 also equal to T1 into S1 minus S0. Since it is asking H1 minus H0, for deciding the H1 minus H0, I should find the S1 and S0 because T1 is given in the problem. Okay. For that, first let us decide the entropy at state 3. Look at the state 3, listen carefully, very very important problem. Look at the state 3. State 3 is lying along the saturated liquid curve. That means at state 3, refrigerant is available as a saturated liquid. For the liquid, entropy at state 3 with respect to 0 state, entropy always decided with respect to 0 degree centigrade, S3 minus S0, otherwise I can also write S3, simply S3. S3 means entropy at state 3 with respect to 0 degree centigrade equal to Cp of the liquid into Ln, temperature at state 3 dividing by absolute temperature corresponding to 0 degree centigrade. That is the formula. Cp of the liquid, look at the Cp of the liquid, 4.8 given, into Ln, T3, T2 equal to T3, that is equal to 310 dividing by T0 need not be given. T0 means here, this T0 is different. This is the temperature corresponding to 0 degree centigrade. Absolute temperature corresponding to 0, not this temperature is what? What a temperature at a 0 state. Otherwise, it is better to avoid this one, right? It is better to avoid this one. Otherwise, you are confusing. Otherwise, I can 0. Okay, 1 minute. This is the T, right? T0, no problem. This is the temperature, absolute temperature at 0 degree centigrade. Absolute temperature at 0 degree centigrade, 273.15, roughly 273. Simplify this value for getting the S3. My calculator has shown 0.61 kilojoules per kilogram Kelvin. This T0 is differing from this T0. This T0 I marked corresponding to that state. This T0 is the temperature at 0 degree centigrade. Okay, right. Now S3 I got it. Then as you know, H2 minus S3 equal to T2, S2 minus S3. By using this formula, you can decide the entropy at state 2, because already you got the entropy at state 3. Now H2 minus H3 equal to temperature, right, in the 2 to 3 process into S2 minus S3. H2 minus H3 given, H2 minus H3 is the latent heat, that is the 1054. 1054 is equal to 310 multiplied by S2 is unknown value minus S3, just now I got it 0.61. From this you can decide the S2 value. My calculator has shown S2 4.01 kilojoules per kilogram Kelvin. That is S2. Okay. But look at the 1-2 process. This 1-2 process is maintaining constant entropy. Therefore, S2 equal to S1. S2 equal to S1. This S2 is equal to S1 is equal to 4.01 kilojoules per kilogram Kelvin. Now for finding the H1 minus H0, already I got S1. I need to decide the entropy at 0, state 0. For that, entropy at state 0 with respect to 0 degree centigrade is, right, again look at the state 3, state 0. The state 0 also lying along the saturated liquid curve. Along the saturated liquid curve, liquid is available. For a liquid, right, entropy formula, specific heat of the liquid into Ln, temperature corresponding to 0 state, dividing by temperature corresponding to 0 degree centigrade. Temperature corresponding to 0 degree centigrade. This is also 0 degree centigrade. Okay. It is equal to, specific heat of the liquid is 4.8 given, Ln, temperature at 0, state 0 is given, 260 Kelvin. 260 divided by absolute temperature corresponding to 0 degree centigrade. 0 degree centigrade is the reference state for deciding the entropy, that is 273. Simplify it for getting the entropy at state naught minus 0.23. Definitely it is negative because 260 by 273 is a fractional value. Ln fractional value always negative. My calculator has shown minus 0.23 kilojoules per kilogram Kelvin. That is S naught. Then what is the H1 minus H naught? Here H1 minus H naught is equal to temperature at state 1 into S1 minus S naught. Temperature at state 1 260 Kelvin, 260 Kelvin into S1. Where is the S1? Of course, S1 equal to S2, 4.01. 4.01 minus of minus 0.23. You simplify this value for getting the answer. My calculator has shown 1103.44 kilojoules per kilogram. That is the enthalpy difference between the state 1 and naught. I hope all of you clearly understood. That is the answer. Understood clearly? Yes. Right? It is one of the gate problems. Okay. Answer is, okay, range given 10952 1130. Our answer is 1103.4. 1103.44. 1103.44. Absolutely correct. Understood clearly? Yes. Similarly, look at the another one. It is asking like this. In a compression ignition engine, means diesel engine, the inlet air pressure is 1 bar. That means for the diesel cycle, inlet pressure given, and pressure at the end of the isentropic compression is 32.42. It is better to mark the PV diagram for cycle of the diesel engine or compression ignition engine. The diesel cycle is the theoretical cycle for the practical compression ignition engine. Look at the different process. Diesel cycle consists of isentropic compression followed by constant pressure heat addition followed by isentropic expansion followed by isochoric heat rejection. That is the diesel cycle. Pressure at the beginning of the compression P1 given, pressure at the end of the isentropic compression P2 given. Look at the P1, P1 1 bar, P2 32.42 bar. P1 1 bar, P2 32.42 bar. Next, the expansion ratio is 8. It is given expansion ratio RE equal to 8. Assuming the ratio of specific heats, that is gamma 1.4, adiabatic index gamma equal to 1.4. The air standard efficiency in percentage, you are asked to decide the diesel cycle efficiency. You know diesel cycle efficiency formula 1 minus 1 by RC power gamma minus 1 into rho, rho is the cutoff ratio, rho power gamma minus 1 by gamma into rho minus 1. Here right, only gamma is given, compression ratio not given, cutoff ratio also not given, means we need to decide it. For that, first let us decide the compression ratio. Since 1 to 2 is the isentropic compression process, for that process P1 V1 power gamma equal to P2 V2 power gamma. Let me mark the V1 and V2. This is the volume before compression and this is the volume after compression. And this is the piston displacement volume, is also called swept volume, is equal to V1 minus V2. Anyhow, The quantity V1 by V2 is called compression ratio. Therefore, it can be written as P2 by P1 is equal to V1 by V2 power gamma. Can also be written as V1 by V2 equal to P2 by P1 power 1 by gamma. The quantity V1 by V2, this quantity you are calling as compression ratio RC. RC equal to P2 by P1. Look at the P2, 32.42 divided by P1, 1 power 1 by gamma given 1.4. Simplify it for getting the compression ratio. My calculator has shown the compression ratio exactly 12. Compression ratio 12. Right? Then, as you know, the cutoff ratio rho equal to ratio between the compression ratio and expansion ratio. Ratio between the compression ratio and expansion ratio is the cutoff ratio. Compression ratio you got 12, expansion ratio given 8. Simplify it for getting the rho value. My calculator has shown 1.5. That is the cutoff ratio. Then diesel cycle efficiency equal to 1 minus 1 by compression ratio power gamma minus 1 into rho power gamma minus 1 by gamma into rho minus 1. 1 minus 1 by, look at the compression ratio is 12. 12 power 0.4 into rho value 1.5 power 1.4 minus 1 divided by gamma 1.4 into rho 1.5 minus 1. Simplify this value. Since it is asking in percentage, multiply with 100. Multiply with 100. My calculator has shown 59.6 percentage. 59.6. 59.6 percentage. That is the answer. Simple problem, but we need to decide the compression ratio and cutoff ratio. Understood clear? Are you following clearly? Yes. Then look at the next one. Again MSQ type question, asking like this: which of the following statements is / or correct? Reactive turbine is a pressure compounding turbine. Absolutely correct. Curtis turbine is the velocity compounding impulse turbine, whereas reactive turbine is the pressure compounding impulse turbine. Option A is correct. Reheating of steam in steam turbine power plant is to reduce the moisture in the lateral stage of the turbine. Yes. The main intention of the reheating of the steam turbine power plant is for minimizing the moisture content, that is liquid particles formation in the last part of the expansion. Whereas the reheating of the gas turbine power plant is for increasing the turbine work. Of course, by reheating the steam with the steam turbine power plant, turbine work increases, but that is not my main motto. My main motto of reheating the steam for the steam turbine power plant is to increase the dryness fraction or to minimize the moisture content in the last part of the or lateral stage of the turbine. Therefore, B also absolutely correct. Look at the C. For the same blade speed, D-level turbine maximum work is 2 times that of partial. Absolutely correct, because the maximum work of the D-level turbine is 2U square, whereas the maximum work of the Parsons turbine is just U square. It is clearly given for the same blade speed. For the same blade speed, definitely you can conclude that the maximum work output of the D-level turbine is 2 times the maximum work of the Parsons turbine. That's why it is given. Once again, let me read the question. For the same blade speed, D-level turbine maximum work is 2 times the 2 times that Parsons. Yes, absolutely correct. C correct. C correct. Parsons turbine is a pure reaction turbine. No, Parsons turbine is the impulse reaction turbine. Hero turbine is the pure reaction turbine. Pure reaction turbine is not practically possible. Even in the hydraulic machines like Francis turbine, Kaplan turbine, propeller turbine, they are also not pure reaction turbines, right? Francis turbine, Kaplan turbine, propeller turbine are the impulse reaction turbines for water turbine power plant. Like how the Parsons turbine is the impulse reaction turbine or practical reaction turbine for the steam turbine power plant, where the turbine is driven by the combined effect of impulse force and reaction force. Anyhow, D is absolutely wrong. Only A, B, C correct. Are you following clearly? Yes. Then look at the next one. It is asking like this: which of the following statements is / are correct? At the same pressure, ideal gas occupies more volume than that of real gas. Absolutely correct. You know, the molecular force of attraction, the binding force of attraction for ideal gas is 0. Since there is no controlling force or molecular force of attraction between the ideal gas molecules, the molecules which are present in the ideal gas very freely migrating from one location to another location. Because of that free migration, volume occupied by ideal gas always more than the volume occupied by real gas at the same pressure. The statement A, option A is absolutely correct. Otherwise, let us read the option A once again. At the same pressure, ideal gas occupies more volume than real. Absolutely correct. Sum of the mole fractions is more than 1. No. Sum of the mole fractions equal to 1. Sum of the mass fractions also equal to 1. So B not correct. Sum of the mole fractions equal to 1, not more than 1. Similarly, sum of the mass fraction also equal to 1. Mole fraction, right, and pressure fraction both are equal. Next to the ratio between Cp and Cv is equal to adiabatic index according to Joule's law. The ratio between the Cp and Cv equal to adiabatic index correct only, but according to Rignol's law, not Joule's law. Not Joule's law. According to Rignol's law, the ratio between the Cp and Cv remains constant. That constant is called adiabatic index. Anyhow, C not correct. C absolutely wrong. Look at the D. The ratio between universal gas constant and characteristic gas constant is equal to its molecular weight. Absolutely correct. Because as you know, the gas constant R equal to Ru by M. Or I can say the product of molecular weight and gas constant is another constant called universal gas constant according to Avogadro's law. From this, molecular weight equal to universal gas constant divided by characteristic gas constant. From that you can conclude that the ratio between the universal gas constant and characteristic gas constant is equal to its molar mass or molecular weight. That is given. The ratio between the universal gas constant and characteristic gas constant is equal to molecular weight. Absolutely correct. A and D are correct. A and D are correct. Okay, na? Yes. Similarly, next one. Look at this one. Which of the following statements is / are correct? Supersonic flow may maintains normal shock waves. Absolutely correct. Normal shock waves are the characteristics of the supersonic flow only. That's why normal shock waves are found. Only one normal shock wave is found in the diverging part of the converging diverging nozzle. You cannot find normal shock wave either in the throat section or in the converging section, because in the converging section the flow velocity less than sound velocity, that kind of flow is called subsonic flow. But in the diverging section of the converging diverging nozzle, the flow velocity more than sound velocity, that is called supersonic flow. The supersonic flow may prone to the normal shock. That means normal shock waves are characteristics of the supersonic flow. Option A is absolutely correct. Next, look at the B. Checked, not checked, choked flow. It is a printing mistake. Choked flow means minimum constant mass flow rate. No, choked flow means maximum constant mass flow rate, not minimum. B is absolutely wrong. Next, when supersonic flow enters to a converging duct, it may act as diffuser. When subsonic flow enters to, not supersonic, when subsonic flow enters to converging duct, it may act as diffuser. No, when subsonic flow is entering to the converging section, the converging duct is acting as a nozzle, not diffuser. The diverging duct for subsonic flow is acting as diffuser, but it is clearly given the subsonic flow enters to converging duct. When the subsonic flow is entering to converging duct, the converging duct is acting as a nozzle, not diffuser. C is absolutely wrong. Next, reversed Brayton cycle is having two isentropic process and two isobaric process. Absolutely correct. Reversed Brayton cycle means Bell-Coleman cycle. Bell-Coleman cycle is the air refrigeration cycle maintaining two reversible adiabatic type isentropic process and two constant pressure process. Constant pressure process also called isobaric process. D is absolutely correct. A and D are correct. A and D are correct. Okay? Are you following clearly? Yes. Similarly, look at the next one. It is asking like this. Which of the following statements is / are correct? At optimum speed ratio, steam turbine maintains maximum work and maximum efficiency. Absolutely correct. At optimum blade speed ratio, right? The work available from the turbine, is maximum and efficiency also maximum, right? But remember, each and every turbine is maintaining its own optimum blade speed ratio. At its own optimum blade speed ratio, look at the Parsons turbine. For the Parsons turbine, optimum blade speed ratio cos alpha, whereas for the D-level turbine, cos alpha by 2. Similarly, Pelton wheel is also maintaining its own optimum blade speed ratio. At its own optimum blade speed ratio, the turbine can maintain the maximum work output and maximum efficiency. A correct. Next, at optimum compression ratio, efficiency of Otto cycle is maximum. No, at optimum compression ratio of the Otto cycle, the work output is maximum, not efficiency, right? At optimum compression ratio of the Otto cycle, work output is maximum, not efficiency. B is wrong. Next, at optimum pressure ratio, the work output of the Brayton cycle is maximum. Absolutely correct. The optimum pressure ratio of the Brayton cycle, it can maintain the highest work. C correct. Next, C correct. Look at the D. For the same cycle temperature limits, work output of the Brayton cycle is equal to that of Otto cycle. No, you know the net work output of the Otto cycle equal to, right, expansion work minus compression work. Expansion work and otherwise I can also write 1 minute. The net work output of the Otto cycle is equal to heat supplied minus heat rejection. Network output of the Brayton cycle also equal to heat supplied minus heat rejection. But heat supplied and heat rejection both are connected to constant pressure process Cp, whereas for Otto cycle both are connected to constant volume Cv. For the same cycle temperature limits, since Cp is more than Cv, therefore for the same cycle temperature limits, I can say that the maximum network output of the Brayton cycle is more than network output of the Otto cycle. But it is given that for the same cycle temperature limits, the work output of the Brayton cycle is equal to, no, D absolutely wrong, right? Look at the last problem. Look at this one. Which of the following statements is / are correct? Relative humidity decreases with sensible cooling process. No, right? Look at the psychrometric chart. Right? So this is the sensible cooling process. In the sensible cooling process, the right state 2 is moving towards the saturation curve. That means relative humidity increases. That means relative humidity increases with a sensible cooling process. A is wrong. Dry bulb temperature increases in the chemical dehumidification process. Definitely during the chemical dehumidification process, dry bulb temperature increases. But wet bulb temperature remains constant. When warm saturated air is cooled, its relative humidity increases. No, the warm saturated air is available along the saturation curve. When the warm saturated air is cooled, right, it can maintain the constant relative humidity. Relative humidity cannot be changed. When warm saturated air is cooled, its relative humidity increases. No, C wrong. Look at the D. Look at the last option. For the saturated air, wet bulb depression is 0. Absolutely correct. Because wet bulb depression equal to wet bulb depression. Wet bulb depression equal to difference between the dry bulb temperature and wet bulb temperature. For the saturated air, both the dry bulb temperature and wet bulb temperature are equal. Therefore, wet bulb depression is 0 for saturated air. D is correct. Here A and D are absolutely correct. Not A, एक minute, not A, B and B and D are absolutely correct. I hope all of you clearly understood. With this I am concluding. All the best and God bless you.